This presentation will address the topics of energy and heat capacity. Energy is defined as the ability to do work or transfer heat. Heat is defined as the form of energy that flows due to a temperature gradient. For example, heat will flow from inside a heated home during winter towards the outside of that home, because the temperature on the inside is higher than on the outside. For now, it suffices to say that energy is energy no matter where it comes from. What changes is the label we put in the energy to identify its origin. Labels such as kinetic, for energy, contained by virtue of being in motion, and electrical, for energy resulting from the flow of electric charge. The best advice I can give is to picture energy as a three-dimensional quantity, with the absolute thermodynamic temperature as the vertical dimension. On the right side of this slide, I have included a picture of what energy would look like to someone with a good imagination. We previously mentioned the term thermodynamic scale. A thermodynamic scale is independent of the properties of any one substance. For example, the Fahrenheit temperature scale, first proposed by David Gabriel Fahrenheit, is defined by 2 points. 0 Fahrenheit, being the lowest air temperature recorded at Fahrenheit's hometown, Danzig, during the winter of 1709. This 0 point is based on an arbitrary set of conditions and does not qualify as a true thermodynamic parameter. On the right side of this slide, I have included a picture of a temperature scale. You will notice that on this scale the molecular motion is a function of the temperature, and the molecular motion approaches 0 when the temperature approaches 0. This is called the Kelvin temperature scale, named after the English scientist, Lord Kelvin. We say this is an absolute temperature because the absolute 0 point does not depend on the properties of any one substance. Absolute 0 does not even depend on where you are. The absolute 0 is the same thing here, and at a different galaxy across the known universe. Calculations done for this presentation use either Celsius or Kelvin degrees. We will be computing energy changes rather than absolute energies. The distinction between Celsius and Kelvin degrees is irrelevant in this context. Equation number 01 helps clarify this fact. Here we can see that the Celsius temperature is similar to the Kelvin temperature. The only difference being that the 0 value for the Kelvin scale is shifted relative to the 0 value of the Celsius scale. We cannot use Fahrenheit degrees directly, because the scale is not only shifted but also the size of the Fahrenheit degrees is different than the Kelvin degrees. On the right side of this slide, I have included a graph with the equation of the straight line in standard format. The vertical axis displays the Fahrenheit degrees. The horizontal axis displays the Celsius degrees. The slope of such a line is the ratio Fahrenheit to Celsius, which is 1.8. The y-intercept of the line is 32 Fahrenheit. This is the Fahrenheit temperature equivalent to 0 Celsius. If you put all the information together and use the standard y equals mx plus b notation, you will get equation number 02. This is the equation that converts between Fahrenheit and Celsius temperature scales. Here are some questions to think about. What is a thermodynamic scale? Would the boiling point of water qualify as a reference point for a thermodynamic scale? What is the definition of absolute 0? For those of you who prefer more interesting questions, here is this one. The temperature during a New York winter can sometimes drop to 27 Fahrenheit. Compute the Celsius and Kelvin degree equivalent of 27 Fahrenheit. We start by using equation number 02. This will convert Fahrenheit to Celsius. It is best if all the labels are included in the equation. Dimensional analysis will lead you to the right answer as long as all quantities are labeled. First, we do the addition or subtraction part. Here, the 32 Fahrenheit is moved from the right side to the left side of the equation. Now the 32 Fahrenheit are subtracted from 27 Fahrenheit. Then, the 1.8 Fahrenheit to 1.0 Celsius ratio is moved from the right side to the left side of the equation. Now the ratio is inverted, so the Fahrenheit will cancel. After doing all the math, our answer is negative 2.8 Celsius degrees. This is cold enough to turn water into ice, then make the ice shatter due to expansion. For the Celsius to Kelvin conversion, we use equation 01. The 273.15 is added to the minus 2.8 Celsius to obtain 270.4 Kelvin. The SI unit of energy is the joule, denoted by uppercase J. The unit is named after the English scientist James Prescott Joule. His other occupation was brewing alcohol. This instilled in him a keen interest in processes involving temperature and thermal energy transfer. His attention to detail is unmatched in the context of his time period. The joule is a derived unit. It is a product of force and distance. The SI unit of force is the Newton. The Newton is also a derived unit. It is a product of mass and acceleration. The unit is named after the English scientist Isaac Newton. The acceleration can be further broken down into base SI units. In conclusion, the joule is equal to kilogram times meter per second squared times meter. Other common units of energy include the standard calorie, the food calorie, the British thermal unit, and the electron volt. You will notice from the conversion factors provided that the food calorie is simply another label for a kilocalorie, that is, the standard calorie times 1000. The electron volt is often used to report the mass of elementary particles, using Albert Einstein's mass to energy equivalency. You will find the masses reported as electron volt divided by c squared, where c is the speed of light. As an example, consider the situation where 772.0 pounds of mass are lifted a vertical distance of 1.00 feet. The mass will need to overcome the force of gravity to reach the 1.00 feet height. We start by converting the mass and vertical distance into their SI unit equivalents. Here we use the ratio 0.454 kilogram to 1.00 pounds of mass. The pounds of mass cancel to give 350.5 kilograms. Then we use the ratio 0.3048 meters to 1 foot. The feet cancel and we get 0.3048 meters. We keep all digits in the answer and wait until the end to round off. Then, we use the equation for potential energy on the Earth's gravitational field. In order to obtain the answer in units of joules, the mass must be in kilograms. The acceleration due to gravity must be in meters per second squared. This gives a force in newtons. Finally, the height must be in meters. So all the units will match to give an answer in joules. Here we get 1048 joules as the potential energy stored by lifting 772.0 pounds of mass by a vertical distance of 1.00 feet. The previous example used data reported by James Prescott Joule in 1843. If you take the data shown here, you would obtain the heat capacity of water. That is 4.18 joules per degree times gram. This slide contains a lot of information. Those paying attention will notice the term adiabatic. Here it means that all of the energy released by 772.0 pounds of mass falling a distance of 1 foot went into heating the water. There is no such thing as laboratory conditions that will make a process 100% adiabatic. But we can make a process nearly adiabatic by using some tricks. The trick used here is letting the mass fall, then measuring the temperature quickly. This action has the effect of reducing the amount of energy that will be lost to the surroundings. Those paying attention will also notice that the energy has the label uppercase U to indicate this is an internal energy. This is one of 4 so-called thermodynamic potentials. Recall that energy is energy no matter where it comes from. The 4 thermodynamic potentials are all energies, but they have different labels to indicate the conditions under which the measurement was carried out. The 4 quantities called thermodynamic potentials are useful in the chemical thermodynamics of reactions and non-cyclic processes. They are internal energy, the enthalpy, the Helmholtz free energy, and the Gibbs free energy. The 4 thermodynamic potentials are related by offsets of the energy from the environment, meaning that the difference between them comes from the configuration term, Ts, and the expansion work term, PV. Even if you do not understand the thermodynamic principles involved here, it is recommended that you understand that you will find energy terms with different labels. All energy terms describe the same entity, measured under different conditions. Here are some concepts to think about. Thermodynamic temperature is the absolute measure of temperature and is one of the principal parameters of thermodynamics. Thermodynamic temperature is defined by the third law of thermodynamics, in which the theoretically lowest temperature is the null or 0 point. This we have defined as 0 Kelvin or minus 273.15 Celsius. Temperature is a measure of the average kinetic energy of the particles in a sample of matter expressed in units or degrees, designated on the thermodynamic scale. This explains our earlier suggestion about picturing energy as a three-dimensional quantity with temperature as the vertical dimension. The other 2 dimensions, comprising the cross-sectional area of the energy, is the heat capacity or specific heat. A detailed review of the thermodynamic principles of heat capacity is beyond the scope of this presentation. What I expect you to understand is that when we define temperature as the average kinetic energy of the particles in a sample, we were referring to what is illustrated in the lower right corner of this slide. Here, we have a molecule, and the kinetic energy is the energy contained in a molecule by virtue of being in motion. 3 types of motion are illustrated: translation, rotation, and vibration. This is how the molecules store energy. And when the temperature goes up, the translational and rotational motion gets faster and the vibrational frequency increases. Also, notice the 2 equations near the middle of the slide. There are 2 quantities labeled C subscript P and C subscript V. An experiment done in a container open to the atmosphere is referred to a constant pressure process, and the term C subscript P applies. An experiment done in a sealed container is referred to a constant volume process, and the term C subscript V applies. A good example is the combustion of gunpowder. If you ignite the gunpowder in a container open to the atmosphere, you will have built an incendiary device. However, if you ignite the gunpowder in a sealed container designed to break at certain pressure, you will have built an explosive device. This explosive device is clearly more powerful than the incendiary device. The difference comes from whether or not the energy from expansion was harvested. An experiment done in a coffee cup calorimeter is classified as a constant pressure process. The one thermodynamic potential you would be measuring is labeled uppercase H for enthalpy, a word derived from the Greek language. The word enthalpy literally means heat content. When we described the four thermodynamic potentials, there was mention of the creation of a system. The absolute value of a thermodynamic quantity is not something we can measure in an experiment. What we measure is the change in that thermodynamic quantity. The figure here will help illustrate this fact. To the left, we have an absolute enthalpy, with a vertical dimension set equal to the thermodynamic temperature. This includes the entire temperature range, starting from absolute zero up to the temperature of the system at this point in time. To the right, we have a slice of enthalpy with thickness, delta T. Here we have a measurable quantity, called thermal energy in transit, or simply heat. This quantity is labeled with an uppercase Q and is the product of the measured temperature change and the heat capacity of the system, which needs to be known beforehand. If a process does not involve expansion or compression of the system, the heat term is the only component of the enthalpy change delta H. Thermodynamic quantities have two components, a numerical value with units, and a positive or negative sign. Consider two interacting systems, labeled System 1 and System 2. Let's consider an amount of thermal energy moving from System 1 towards System 2. From the perspective of System 1, the energy is being lost, and the sign of the thermal energy, Q, is negative. From the perspective of System 2, the energy is being gained, and the sign of the thermal energy, Q, is positive. In conclusion, there is no such thing as negative energy. The sign in front of the thermodynamic quantity depends on the perspective from which the energy transfer is observed. We summarize the parameters involved in the process of heat transfer. In equation 3, this is the thermal energy transfer equation. The thermal energy is obtained as the product of sample mass, specific heat capacity, and the change in temperature. The specific heat capacity dictates how much energy a certain amount of material will absorb or release in order to induce a 1-degree change in temperature. For example, consider water and gold. Because the specific heat capacity of water is about 30 times the specific heat capacity of gold, the same amount of thermal energy that increases the temperature of 1 kilogram of water by 1 degree will increase the temperature of 1 kilogram of gold by about 30 degrees. An alternate form of equation 3 combines the mass and specific heat capacity into a single term, C. From this we get equation 4. This form of the equation would be the one used for an object of fixed mass. Because the mass of the object is fixed, the mass is already built into the heat capacity term. Here are some questions to think about. How would you define heat capacity? Based on atomic or molecular motion, how do you explain that liquids have higher heat capacities than solids? For those of you who prefer the more practical examples, consider a 25-watt soldering iron coming into contact with a copper pad of mass 0.375 grams for a period of 5 seconds. The copper pad heats up from room temperature, which is 20 Celsius degrees, to the temperature required to melt certain type of soldering flux, which is 300 Celsius degrees. Compute the heat transfer parameter, Q, from the perspective of the soldering iron and the copper pad. Compute the power output rate of the soldering iron in units of watts. We start by selecting the equation that applies. Because the mass of the copper pad is given, we use equation 03. We first substitute the information into the variables of equation 03. We use 0.375 grams for the mass. We use 0.380 joules per gram times degree for the specific heat capacity. And we use 300 Celsius degrees for the final temperature and 20 Celsius degrees for the initial temperature, respectively. We let dimensional analysis take care of the rest. First, the units of mass, the grams, cancel with the grams in the specific heat capacity. The product of mass and specific heat capacity give a quantity with units of joules per degree. This is called heat capacity without the word specific in it. We then subtract the two temperatures to get the temperature change. Now the degrees in the temperature change cancel with the degrees in the heat capacity. The only remaining label is now the units of energy, the joules. We get our answer, which is 39.9 joules. For the next part of the question, we consider the concept of perspective mentioned earlier when discussing thermal energy transfer. The thermal energy transfer has a value of plus 39.9 joules from the perspective of the copper pad, because the copper pad is gaining energy. The thermal energy transfer has a value of minus 39.9 joules from the perspective of the soldering iron, because the soldering iron is losing energy. For the last part of the question, we use the definition of the watt. This unit is named after the Scottish scientist James Watt. The watt is the SI unit of power equivalent to 1 joule per second, corresponding to the power in an electric circuit in which the potential difference is 1 volt and the current 1 ampere. We put together the 39.9 joules of the copper pad absorbed in the 5 seconds the soldering iron was in contact with the copper pad. This gives the power output rate of the soldering iron. Those paying attention will notice that the information we got clearly stated that this soldering iron has a power output rate of 25 watts. But here we get only 7.98 watts. This is because the 25 watts refer to the entire power output of the soldering iron. This includes the heat that is constantly dissipating into the surroundings. As a result, only a fraction of the 25 watts actually went into heating the copper pad. Experiments in thermal energy transfer involve two interacting systems coming into thermal equilibrium. For example, consider two bodies of water. Both have the same mass, but their temperatures are different. The two systems are insulated from the surroundings, but can exchange energy through a thin wall separating the two. The temperature gradient is the driving force being the energy exchange. The system of lower temperature will gain energy, and the system of higher temperature will lose energy. When the two systems reach the same temperature, they are said to be in thermal equilibrium, and the net energy exchange between them will become zero. When we have two interacting systems with two sets of data, we need to write equation 03 in a different format. We can label the two sets of data by using lowercase letters for system 1 and uppercase letters for system 2. As a practical example, consider two amounts of water at different temperatures coming into thermal equilibrium inside an insulated container, such as a high-quality isobaric calorimeter. The cold water has a mass of 25.0 grams and an initial temperature of 20 degrees Celsius. The hot water has a mass of 15.0 grams and an initial temperature of 60 degrees Celsius. We use the form of a heat transfer equation that contains variables for two interacting systems. We first substitute all the information we have into the variables. Here we have used lowercase labels for the cold water and uppercase labels for the hot water. As always, it is best to cancel the units one by one. Here we first cancel the mass to obtain the heat capacity terms in joules per degree. How you proceed from this point on depends on individual preferences. You can treat this as a standard algebra problem, but you must never forget that chemistry is not pure mathematics. We will take the approach that requires a basic understanding of the thermodynamics at work. We know that the hot water will transfer thermal energy to the cold water. The amount of energy released or absorbed is directly proportional to the heat capacity of each system. Here we can isolate the heat capacity terms on the left side of the equation and the temperature change terms in the right side of the equation. When we do this, all the units cancel and we get a quotient or ratio on each side of the equation. We get that 1.67 is equal to the ratio delta T of hot water to delta T of cold water. This is our answer. All we need to do is interpret it in a way that returns an answer in Celsius degrees. The 1.67 means that the temperature of the hot water changed 1.67 times as much as the temperature of the cold water. In other words, every time the cold water temperature increased by 1.00 degrees, the hot water temperature decreased by 1.67 degrees. We then take the difference in temperature between the hot water and the cold water. The temperature we are looking for is between these two. We then distribute the 40 degrees temperature difference the same way we would do a mass percent distribution. Here we get 25 degrees of change for the hot water. We know the hot water lost energy, so we know the final temperature is 60 Celsius degrees minus 25, which is 35 Celsius degrees. We can do a similar calculation for the cold water and get 15 degrees as the answer. We know the cold water gained energy, so we know the final temperature is 20 Celsius degrees plus 15, which is 35 Celsius degrees. This is the same answer we got using the information from the hot water. Another way of solving the problem is straightforward, but the science behind the process is mostly lost. Here, we need to include a negative sign on front of one of the systems. It is standard practice to write the negative sign on front of the parameters of the system that is losing energy. This does not mean the energy is negative. This just means the energy has the opposite sign as compared to the other side of the equation. The problem is slightly simplified by the fact that the final temperature is a common parameter once the systems reach thermal equilibrium. Notice that the answer is still 35.0 Celsius regardless of the way we choose to solve the equation. An experiment to determine the specific heat capacity of a metal requires a coffee cup calorimeter. The formal term is actually isobaric calorimeter. The term isobaric means that processes occur at constant pressure. That is, whatever the atmospheric pressure is at the time and place the experiment is done. An energy change measured under constant pressure conditions is called enthalpy, one of the four thermodynamic potentials mentioned earlier. In order to follow the pattern we already established, a sample of material or system of particles under observation will be labeled System 1, and the water in the calorimeter will be labeled System 2. In our previous example, the equilibrium temperature of a water mixture was computed. One assumption was made to simplify the problem. This assumption was that all of the thermal energy was exchanged between two systems, perfectly insulated from the surroundings. This is not true in real experimental settings. The coffee cup calorimeter has a small heat capacity that makes it absorb part of the thermal energy. For example, consider an experiment done to determine this heat capacity. In this instance, all parameters are known from experimental measurements and the energy in transit, Q, can be computed for the two interacting systems. If the calorimeter was a perfect insulator, the two Q values would match. You can pause the video and do the calculations. The result you will get is that the hot water lost 8,988 joules of energy, and the cold water gained 8,384 joules of energy. There are 604 joules of energy unaccounted for. This we have labeled as missing. This is actually the amount of energy that was absorbed by the calorimeter. The 604 joules that are unaccounted for are used to compute what we call the calorimeter constant. This parameter will dictate how much energy will go in or out of the calorimeter every time the temperature changes by 1 degree. The initial temperature of the calorimeter is taken as being the same as the temperature of the water initially held inside. The final temperature of the calorimeter is the same as the equilibrium temperature of the two systems held inside the calorimeter at the end of the experiment. In this instance, we get a heat capacity equal to 18 joules per degree. Here we have used equation 04, which applies to an object of constant mass. The calorimeter constant would be included when doing calorimetry work that requires precise measurements. Including this term gives us equation 05. The difference between omitting or including the calorimeter constant is normally plus or minus 5%, and this is mostly ignored in general chemistry experiments. We show here a setup for the experiment to determine the specific heat of a metal. A known mass of water is placed inside a coffee cup calorimeter. For this example, assume the mass of water is 32.0 grams and its temperature is 24.0 Celsius degrees. A metal sample of known mass is brought into thermal equilibrium with a hot water bath. Measuring the temperature of the water bath is the same as measuring the temperature of the metal sample. The metal sample can consist of a collection of small metal beads or fragments. For this type of material, the sample can be placed inside a test tube, which in turn goes inside the water bath. For this example, assume the metal weighs 11.5 grams and its temperature is 94.0 Celsius degrees. The metal is quickly transferred from the water bath to the calorimeter. The metal and the water come into thermal equilibrium inside the calorimeter, and the temperature is measured at 5-second intervals for 1 minute. The data can be plotted into a thermograph by taking the highest temperature reading in the set as being the equilibrium temperature is good enough for most situations. We then put all the data into the thermal energy transfer equation. The metal is assigned the Q value with a negative sign. The experiment provides all the values for all the variables except the specific heat of the metal. We solve the equation by isolating the specific heat capacity term on the left side and all other terms on the right side. If everything has been done correctly, the units in the answer are joules per gram times degree. Here we get a specific heat capacity equal to 0.521 joules per gram times degree. I leave it to you to guess what metal has that specific heat capacity. For calorimetric measurements that require the highest accuracy, the calorimeter heat capacity must be determined from a calibration step. Consider a calorimeter whose heat capacity has being measured as 9.50 joules per degree. This calorimeter is filled with 25.0 grams of water at a temperature of 20.0 Celsius degrees. A metal sample of mass 21.0 grams and temperature 90.0 Celsius degrees is quickly transferred to the calorimeter. After reaching thermal equilibrium, the metal, the water and the calorimeter have a temperature of 25.0 Celsius degrees. From that information, the specific heat capacity of the metal can be determined. We start by setting up the thermal energy transfer equation with a Q parameter for the metal on the left side. The sign of the Q is negative to indicate the metal is losing energy. On the right side of the equation, we have two Q values, one for the water and one for the calorimeter. Next, we expand the equation to include all terms. We substitute all the information into the equation variables. The only unknown should be the specific heat capacity of the metal. For this kind of problem, it is best to solve the right side of the equation first. This gives the thermal energy gained by the water and the thermal energy gained by the calorimeter. If everything has been done correctly, all the units on the right side of the equation cancel except for the energy units, the joules. Here we get that the water absorbed 522.5 joules, while the calorimeter absorbed 47.5 joules, for a total of 570 joules. We then transfer the product of grams times degree from the left side of the equation. Now we have a quotient with joules in the numerator and grams times degree in the denominator. The negative signs cancel because both the answer and the specific heat capacity variable have negative signs. Our final answer is 0.418 joules per gram times degree. I leave it to you to guess what metal has that specific heat capacity. We conclude this presentation with some questions to think about. Why is that the metal sample had to be transferred quickly from the hot water to the calorimeter? The heat capacity of most styrofoam coffee cups is between 5 and 10 joules per degree. How big of an error was introduced by ignoring the calorimeter heat capacity? For those of you who prefer something more challenging, estimate the specific heat capacity of copper, assuming the standard value for theoretical heat capacity, which is 6 calories per mole times degree. Copper has a molar mass of 63.55 grams per mole. You can pause the video and try it. Here is the answer. I did not think anyone would pause the video because I do not believe there is honorable people left in this world.